So I should introduce the term level scheduling. So this whole idea of finding which things can be done in parallel by levels is called level scheduling. The algorithm for finding the level structures is called level scheduling. Okay. And the same idea, so level scheduling, I'll call it LS. Level scheduling can also be used to parallelize static pattern ILU factorization. But not threshold-based ILU factorization. And the reason for that is because the sparsity pattern is not known in these threshold algorithms. But once the triangular factors are computed here, then it can be parallelized using level scheduling. Okay? All right, so let me move on to a related way of parallelizing the incomplete factorizations. And it's a way of trying to introduce more parallelism. So we saw from that grid problem that we had, let's say the 100 by 100 grid, we have a large number of levels. We have 199 levels. Each level has to be done sequentially. There's a way of reordering. So there's that magic thing that we've been talking about. Reordering the problem such that we can reduce the number of levels of the original problem. Okay? Once we have the triangular factors, we cannot reorder, right? Because triangular factors have to stay triangular. We cannot reorder. But we can try to reorder the original problem so that it has more parallelism. So the idea we're going to be using is called multicoloring. And you can't apply it directly. If you already have the factors, you can't apply this method directly. So you have to go back to the problem you're trying to solve. So let's say you're trying to solve AX equals to B. You can solve instead a reordered problem. So that's the reordered matrix where P and Q are permutation matrices. I think last time I wrote P, A, P transpose, so that would be a symmetric permutation. In general, the permutations do not have to be symmetric. Okay, although I will actually use symmetric permutations for the rest of this lecture. Okay, so we can solve this problem instead, and of course we can recover the original solution. So where P and Q are permutation matrices. Such that PAQ has some desirable properties. And in particular, what we would like is we would like PAQ to have a small number of levels. Okay? So here we have our original matrix A. We're going to apply the ILU factorization. We have to do it in 5 steps because there were 5 levels. But can we reorder this matrix PAQ, reorder this matrix A to get PAQ such that the number of levels is different and the number of levels is smaller? Okay, and if the number of levels is smaller, then we have more parallelism. Okay, so let's go back to this example again. And instead of ordering the nodes in the natural ordering, let's consider a different ordering. And actually, no, let me do a slightly larger problem because it'll be hard to do it on a smaller problem. So let's consider this grid, 4x4 grid. Okay, I could number using a natural ordering, but instead of using the natural numbering, let's use another numbering. Like this. I'm just going to use 1, 2, 3, 4, 5, 6, 7, 8. So it's a little bit like a checkerboard. And then 9, 10, 11, 12, 13, 14, 15, 16. Okay, so this checkerboard sometimes called red-black ordering. Okay, because I have some red nodes and I have some black nodes. In this case, it's blue nodes, but red-black ordering. Okay, and let's draw the matrix that comes from this ordering. And what you can do is you can just draw a matrix that is 16 by 16, right? And you draw a non-zero whenever you have a connection in the grid. So you have a non-zero 1, 9, you have a non-zero 1, 11, you have a non-zero 11, 3, etc. Okay? I'm not going to draw the whole thing. But imagine ordering all of the red nodes first and all of the blue nodes or black nodes second. Okay? So this is 1 to 8 and then 9 to 16. So 1, 9 is going to be over here, and 1, 11 is going to be over here, right? And 2, 9 is going to be over here, etc. But in particular, you'll notice that there are no couplings between nodes of the same color. So there are no edges between 2 nodes that are red. Okay, and this block of the matrix describes all of the couplings between the nodes that are red. Therefore, this block is empty except for the diagonal. Okay, so there's the diagonal, but otherwise it's zeros over here. And similarly, in the black part, we also just have a diagonal matrix. And we might have things over here because these are the couplings between the black and the red nodes. Okay, so all the black nodes are decoupled from each other. And all the red nodes are decoupled from each other. All the red nodes are decoupled from each other. Therefore, the matrix has the form D1, D2, A12, A21, where D1, D2 are diagonal. Okay, so now suppose that we have this matrix and we want to apply the ILU 0 algorithm to it. So how many levels are there? Alternatively, take the lower triangular part of this matrix and say we want to solve with the lower triangular factor in parallel. How many levels are there? The answer is the same. Might be easier to think about the triangular solve. So the answer does not depend on the problem size. Okay, doesn't depend on 16 or 8 or anything like that. Any volunteers? So the remarkable, maybe surprising result is that there are only 2 levels. Did anybody see that? Because you can, let's say we're doing the triangular solve, you can solve for all of the red variables at the same time. Right? All of the red variables only depend on, well, they don't depend on anything. Right? So let's look at the lower triangular factor. Right? We look to the left in the row of all the red variables, and there's nothing there. So none of these red variables depend on anything. We can do them all at the same time. Right? And then so that's the first level. And then the second level, we look at all the black variables. They only depend on red variables, but they've already been computed. Right? So all the black variables can be done at the same time. So there's only 2 levels. So that's a remarkable reduction in the number of levels, going from 199 or much larger for a larger problem. By doing this red-black reordering, we've reduced it to 2 levels. And the size of each level is quite large. Right? The size of each level is the total number of variables divided by 2. So there's a lot of parallelism there. Now, if you're given an arbitrary mesh, you cannot color using 2 colors. So 2 colors will work if you have a Cartesian mesh and a 5-point stencil or a 7-point stencil for your differential operator. So red-black ordering works for 5-point and 7-point matrices. In general, we might have to use more colors. So in general, what we want to do is we want to find a coloring of the mesh, meaning we want to choose a color for each node such that no two nodes that are adjacent, no two nodes that are neighbors, have the same color. Okay? And that way we can reorder the matrix such that the diagonal blocks are diagonal. So let me draw a picture of that. So for these 5 and 7 point stencils, we only need 2 colors. For general matrices, more colors are necessary. Okay, so we want to find a color for each node of the mesh or of the graph corresponding to the sparse matrix. Find a color for each node of the graph such that no two adjacent nodes have the same color. Okay. So we might have a meshed, whoa, that's a little bit bad. They're not all triangles. Let me try that again. Okay, so this is not a 5-point mesh, right? So this grid point depends on these neighbors, these neighbors, these neighbors, right, that are connected, right? So we can't use red-black because if we make this one red and this one red, they're connected by the same color. So we have to choose a different color, right? So we want to find a coloring, and finding such a coloring is called multicoloring. And the multicoloring will lead to a matrix of this form where the diagonal blocks are diagonal. So these other blocks, we can't really say what happens, but the diagonal blocks are diagonal. In a multicolor reordered matrix, the diagonal blocks are diagonal. For P colors, so suppose that we found a coloring that was P colors, then we have P diagonal blocks, because we're going to reorder all of the, if we reorder all of the equations with the same, all the nodes with the same color together. Okay, just like we reordered all of the nodes that are red together, we reorder all of the nodes that are red together over here. None of the red nodes interact with each other. All of these diagonal blocks are diagonal. For P colors, we have P diagonal blocks and P levels. So how can we find a multicolor reordering. Let's say we have this example. So someone gives you a matrix. You can construct a graph corresponding to the matrix, and you want to find a color for each graph. So the output is an array. Right? So this is, I think, 16. So it's an array of 16 variables. And for each component of the array, we're going to say, well, what is the color? So what is a way of coloring? Sorry?
2 to the power n.
What is 2 to the power n?
The number of colors.
The number of colors is 2 to the n. What is n? So first of all, how many colors do you think we need for this one? I need to gather 4 different colors. If I think 4 colors, I'm going to need 4 different colors of chalk. So let me collect 4 different colors of chalk. Okay, so an algorithm might work like this. I'll just pick a node and we'll color this one red, right?
If we color the adjacent connected nodes
Yep.
differently and then repeat the same pattern.
Okay. So that one, we have to we can't color it red, so we'll just pick another color, yellow. This one we can't pick red, so pick another color, blue. That one we can't pick red, so we'll pick another color. How about white? Okay. And this one,
Can you use, for the blue one, can you use?
we can also use yellow. All right, we can choose yellow, no problem. We want to choose the fewest number of colors, right? So yellow. Okay. And this one, we could, so one way to do it is randomly choose one and then choose a color. This one we can color anything. This one we can color anything. This one we can color not white and not yellow, so we can do red. Right? So if we can continue on, we could color this one white. And this one could be yellow. And then this one could be maybe we need an extra color now, so maybe we need blue. Okay, so finding a coloring with the minimum number of colors is a really hard problem. Okay, but there are ways of finding a coloring that get us pretty close to the minimum number of colors, and such an algorithm you can just use a greedy algorithm. Meaning you just randomly pick a node and say, well, what color can it be? Just use if the colors are numbered, just use the lowest numbered color, right? You might end up with a really bad situation in which you are forced to choose a color that you don't want to use. So it's sometimes better to just choose one and then look at its neighbors and color, and then look at all of its neighbors and color, something like a breadth-first traversal of the graph, and then color that way. Okay, so finding a coloring with the least number of colors is hard in a computer science way. You want the least number of colors because that reduces the number of sequential steps, right? But greedy algorithms, so greedy coloring algorithms, right? We're just only using local information and coloring based on trying to minimize the number of colors in a greedy fashion. But greedy color algorithms generally give adequate results. Okay. So I've also posted a MATLAB Next program to do coloring. So let me demonstrate that now. So I have a program called Test Multicolor. Okay. And in this program, I'm going to load a matrix from a file. And the matrix, I should show you what it looks like. So this is not a matrix from the sparse matrix collection. It's just a matrix that I created. And what I've done is I have a file that consists of 3 columns. The first column is the I indices, then the j indices, and then the values. Okay. So I can load that into MATLAB. So A is a table with 3 columns, and I can convert that into a sparse matrix. Okay. And I happen to also have the coordinates. So this comes from a finite element discretization over a square. And I happen to have all of those coordinates, so I'm going to load the coordinates, the x, y coordinates, because I want to plot it. So I need to have the coordinates. And on the edges, I have Dirichlet boundary conditions. So they're not connected to anything. So I'm going to remove the connections to the boundaries. And then I'm going to color my, I have this function called Multicolor, which is posted. You can take a look at to see how it works. This will create a vector that colors each one of the vertices using a greedy algorithm. Okay? And then I'm going to plot the graph using my coordinates without the colors first, right? And then I'm going to print out some information about the colors. So let's see how this works. So test multicolor. So I have 4 colors. Okay, here's the graph. So it's a problem over 0, 1, 0, 1. I've removed the boundaries, right? And this is the unstructured mesh. Okay, so I use the unstructured mesh instead of a regular Cartesian mesh because then I could color using 2 colors, right? You've already seen that. That would be boring. And these are the colors. So can you find any 2 nodes that are connected with the same color? So these are different colors. So hopefully you can't. Otherwise, my code would be wrong. And how many colors are there? There's 4 colors, right? And you can also, in this code, reorder the matrix. So this is a relatively easy to understand, but inefficient but easy to understand way of reordering the matrix. We're going to loop over all of the colors. And then for each color, we're going to find the set of indices that have that color. Oh, so this is where I also plotted the colors. Right, I plotted each one with the same color. And then, so that's how I plotted the colors. Oops. And then to do the reordering, I basically do the same thing. So I loop over all of the colors. I find the indices with that color. And then I append all of those indices to my reordering vector. And then I'm going to plot the reordered vector with some lines to show the block partitioning. So that's this. And here's the resulting reordering. Right, so there were 4 colors. These lines show where the each color begin and end, and you can see that the diagonal blocks are diagonal. And if we were to apply a reordering to this, then we'd only require 4 colors. Okay? So let me give you a very simple exercise about level scheduling. So no coding for this exercise. So consider the following. So this is to hand in at the beginning of next class. So consider the following mesh. Okay, so instead of the natural numbering, I'm going to number it in a weird way. I'm going to call this a spiral numbering. I'm going to start over here, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Okay, so there are 25 grid points. This is a spiral numbering. Okay, so the question is, how many levels are there? Okay, and if node 1 is in level 1, what level is node 9? Okay, so just 2 questions. How many levels and what level is node 9? Okay, so you may have to check back in your notes to see how to determine a number of levels. Okay, so that's it. Thank you very much. See you next class.